Hello, it's time for video 2J. The title of this video is Introduction to Continuity. I'm Mr. Miller, and let's get going. So, informally, a function's continuous if you don't have to pick up your pencil when you're drawing it. So, this first graph here, we're doing great until we get to x equals 1. Then we have to pick up our pencil to put a dot here, which is the value of the function at that point, and then pick it up again to draw the rest of it. So that's not a very mathematical definition, but that's kind of the idea of a continuous function. You can draw it without picking up your pencil. So this one's great, except for x equals 1 here. But we got to get used to the mathematical definition here. So a function is continuous if three things are true. The limit exists at that point, the function exists at that point, and the limit and the function are equal to each other. That's what this statement right here is saying. So it actually says a lot. It implies that the limit exists as x approaches some number c. And it implies that the function exists there and that they're equal. So let's go through these points for this graph here at x equals 1. So we see that actually the limit exists at x equals 1. From the left, it's approaching 1, and from the right, it's approaching 1. So the limit does exist. So that point is true. And the function exists. The value of the function is the solid dot here, and the value of the function is 0 there. So the limit exists, and the point exists, or the function exists, but they're not equal. So this one was false. So like we said, the function's not continuous here, because we have to pick up our pencil, but mathematically, because the third condition is not true. Now, this is called a removable discontinuity, because we could fix it. We could define the function to be 1 at that point. That's like moving the dot up here and filling it in. So a discontinuity that we could fix is called removable, and this one's removable. That means we could just redefine the function at that point and fix the problem. Okay, now here's another type of discontinuity. This is an infinite discontinuity, which means that it has a vertical asymptote at the point. So this function is nice and smooth and continuous everywhere except at 2, because it goes to negative infinity on the left, then it has a big jump, an infinite jump, and it goes to positive infinity on the right. So let's check the conditions. So we know that it's not continuous at 2 from the graph, but if we check the conditions, the limit does not exist at the point, so that's a problem. Actually, the function's not even defined at 2. It doesn't have a value there, so that's a problem. And if the limit doesn't exist and the function doesn't exist, they certainly can't be equal, so that's bad. So now, this is an example of a non-removable discontinuity. I can't just fill in a hole in the graph and it would be smooth. So there's nothing I can do about that vertical jump. All right, here's another kind, a third kind. This is called a jump discontinuity. Okay, there's a jump in the graph here. And that happens often with piecewise functions. This is one piece, this is the other piece, and they don't match here at this point. This is actually x equals 2. All right, so does the limit exist at 2? This is the value right here we're looking at. And actually, no. From the left, the function is approaching 6, and from the right, it's approaching 8. So the limit doesn't exist at that point. So it exists from the left and right, but they don't agree. So already it's not continuous there. If any one of these 3 points is false, then it's not continuous. But let's check the others anyway. The function exists at the point. Actually, that's true. That's a solid dot. The function is 6 there. So that one was true. And the limit and the function are equal. Well, if the limit doesn't even exist, they're certainly not equal. So that's false. Now, this is non-removable also, because even though there's a hole there, you might think we could fill it in. It's still got a jump discontinuity here. So this is non-removable. There is at least one other type of discontinuity, but we're going to stick to these 3 for now. Okay, this graph here has an example of all 3 types of discontinuities. So if you look carefully at x equals -2, right here, it has a vertical asymptote. Okay, so if I listed the points of discontinuity, the first one would be -2. The second place, it has a jump at x equals 0. This piece goes down to 1, or it looks like a little bit more than 1. This piece goes to -1. They don't match. There's a jump here. So at x equals 0, there's another discontinuity. And we see a removable one here at x equals 3. There's a hole in the graph, and the function is defined to be this point up here. But if we wanted, we could redefine it, fill in the hole. We could define the function to be 1 at that point instead of way up here at 3, and that would remove the discontinuity. But the way it is, 3 is a discontinuity. Okay, a removable one. Alright, now let's start taking a look at some problems. This is a typical thing we could ask. So we're going to do 4 kind of examples like this. They'll kind of go pretty quickly. In each example, I also had the graph here. If you want, there's a great website, if you haven't heard of it already, at www.desmos, DESMOS.com, where you just type in a function and it'll do all kinds of graphs for you. It's really cool. You can play around with things. So that's where I got the graph of this. So it actually does even better, or almost as good as the TI-89. You can see it better and color the graphs differently. Well, anyhow, we want to find the points at which the function is discontinuous or not continuous. Well, if it's a rational functions are great, except that values that make the denominator 0. And those values are either wholes or asymptotes. So remember, we have to factor it and see what cancels. So the numerator is x plus 2. The denominator factors into x plus 2 times x minus 5. We see the factors of x plus 2 cancel, so x equals -2 is where a hole is. In fact, as x approaches -2, this approaches 1 over -7, and that's that right there. So there's a hole in the graph there. So that's a removable discontinuity. All right, now the factor that didn't cancel, the value of x that goes with that, x equals 5, is a vertical asymptote. I'm just going to put VA for vertical asymptote. And we see it right here. All right, and that would be a non-removable. Nothing we can do about that asymptote. Okay, so there are 2 points. Everywhere else, the function's fine. It's continuous. You don't have to pick up your pen to draw it. But the only places where we would have to do that is at x equals -2 and at x equals 5. Okay, what's next? All right, here's one. Same thing. It's a rational function. We can try to factor the denominator, but it turns out that it doesn't factor. X squared plus 1 is never 0. It's actually always positive. So this function has no problems at all. It's actually continuous everywhere. If you look at the graph, no holes, no vertical asymptotes, so there are no discontinuities. All right, it's continuous on the whole real number line. I think I misspelled that. So it's continuous for x going from -infinity to +infinity. It's continuous everywhere. All right, I like that guy. Here's an interesting one. So on this one, we have the absolute value of x minus 3 divided by x minus 3. It's kind of a weird graph. You have to think about this one to understand the graph. It's actually equal to -1 up to 3, and after that, it's equal to +1. And it's not even defined at 3. At 3, both the numerator and the denominator are 0. So to understand this a little bit, when x is greater than 3, this up here, the absolute value, would be the same as x minus 3. When x is greater than 3, this is positive, and its absolute value is the same thing. So if x is greater than 3, f of x is just x minus 3 over x minus 3. Those cancel, equaling 1 as a whole at 3, which you see. Now if x is less than 3, x minus 3 would be negative. Like if x were 0, 0 minus 3 is negative 3. And the absolute value would be the opposite of the number. So it'd be minus x minus 3 over x minus 3. Because this is negative, and if the number is negative, the absolute value is the opposite of that number. So this cancels, and that leaves just a negative 1, which is what we see here. So this graph has a jump discontinuity at x equals 3. So x equals 3 is the point of discontinuity, and it is non-removable. Okay, nothing we can do about that one. All right, what do we have here? Okay, this one says determine the intervals on which the function is continuous. Kind of a similar question. We got to find where it's not continuous. Okay, well, we're going to do our usual trick when it's a rational function. We're going to factor. So I'm hoping the numerator is x minus 1 times something, and it is. It's x minus 1 times 3x plus 2 over x minus 1. X minus 1's cancel, so there must be a hole there, and you can see it in this graph. What's left is a linear function. 3x plus 2 is a linear function. That's the purple line. Okay, so x equals 1 is a hole, and it's discontinuous there. So that's a removable discontinuity. And they said determine the intervals on which the function is continuous. So for all values of x, up to 1 right here is continuous. It's going to say from negative infinity to 1. I'm going to break out the interval notation here. Union, and then from 1, not including 1, all the way up to positive infinity. So pretty much the only number this doesn't include is the number 1 itself. It goes from negative infinity up to 1, but not including it. From 1, not including 1, all the way up to positive infinity. The only point left out is 1. So those are the intervals on which it's continuous. All right, we've come to our very last example and type of problem. So sometimes they ask us for piecewise functions. It says determine the value of c such that the function is continuous on the entire real line. Okay, in order for it to be continuous, we need the two pieces to match at x equals 2. So for x less than or equal to 2, this one's fine. It's a polynomial. It's continuous. And for x greater than 2, no matter what c is, this is continuous also. The only possible problem can be at 2 itself, where the pieces match. Okay, well, we want them to match. So we want the top function at 2, so that'd be 2 plus 3, to match the bottom function at 2, which would be c times 2 plus 6. And our goal is to find the value of c so that this is true, that the two pieces have the same value at x equals 2. All right, we just got to solve. This would be 5 equals 2c plus 6. If you subtract 6, we get negative 1 equals 2c, or c equals negative 1/2. So if c is equal to negative 1/2, these two pieces will have the same value at 2, and the graph will be continuous. And everybody will be happy. All right, so here's your general assignment. Okay, find the values of x, if any, at which the function is not continuous, and state whether they're removable or not. So 1 is like the examples we did, a rational function. Number 2, you got to see if the pieces agree at x equals 2. If they do, it's continuous. If not, it's not continuous. All right, a lot of math this video. That's good. See you next time.